Imagine standing in front of a machine so enormous that its rotating cutter head is taller than a multi-story building, its body stretches farther than 2 football fields, and its total weight exceeds 2,000 tons. The noise is overwhelming. Steel grinds against solid rock with relentless force, hydraulic cylinders push forward with incredible power, and every movement is carefully controlled by dozens of engineers watching hundreds of computer screens. At first glance, it looks less like a construction machine and more like something built for another planet. Yet this incredible machine spends almost its entire life hidden beneath the Earth's surface, where very few people will ever see it. Every day, while millions of people travel through subway systems, drive through mountain tunnels, or cross underwater rail links without giving them a second thought, one of the greatest engineering inventions in history continues working silently below their feet. This is the tunnel boring machine, better known simply as the TBM. It has completely transformed the way humanity builds underground. Before tunnel boring machines existed, digging tunnels was one of the most dangerous jobs in the world. Engineers relied on explosives, manual drilling, and heavy excavation equipment to slowly carve paths through mountains and solid rock. Progress was painfully slow. Every meter forward brought new dangers. Unexpected rock collapses could trap workers in seconds. Underground water could flood excavation sites without warning. Toxic dust filled the air, making every shift more dangerous than the last. Many tunnel projects took decades to complete, while others were abandoned entirely because the technology simply wasn't capable of overcoming the geological conditions hidden beneath the Earth. Everything changed when engineers developed a completely different approach. Instead of destroying rock with repeated explosions, they designed a machine capable of cutting continuously through almost any type of ground, while simultaneously building the tunnel behind it. The result was nothing short of revolutionary. Modern tunnel boring machines are among the most complex engineering systems ever created. At the front, an enormous rotating cutter head, fitted with hundreds of hardened steel discs, slowly crushes solid granite, limestone, sandstone, and reinforced concrete. Behind it, conveyor systems remove thousands of tons of excavated material every day. Powerful hydraulic cylinders continuously push the machine deeper underground. Robotic arms install massive precast concrete segments that immediately become the permanent walls of the finished tunnel. All of this happens inside one gigantic moving factory, operating hundreds of meters below the surface. Some tunnel boring machines work continuously for years. They travel beneath crowded cities without disrupting life above. They pass underneath rivers, mountains, highways, airports, and even oceans with astonishing precision. Many can maintain their planned route within only a few millimeters over distances of several kilometers. Without these remarkable machines, many of the world's most ambitious engineering projects would never have been possible. Modern metrosystems, high-speed railway tunnels, underwater transportation links, water transfer systems, hydroelectric infrastructure, underground utility networks, all depend on one extraordinary invention hidden beneath the Earth's surface. But despite their enormous size and incredible power, tunnel boring machines face challenges that most people never imagine. How can a machine weighing thousands of tons survive crushing underground pressure? How does it continue operating when geology changes from soft soil to solid granite within only a few meters? And how do engineers guide such an enormous machine beneath some of the busiest cities on Earth without damaging a single building above? To answer those questions, we first need to look inside one of the greatest engineering marvels ever built. Because once you understand how a tunnel boring machine really works, you'll realize it is far more than a giant drill. It is one of the most important machines shaping the future of modern civilization. At first glance, a tunnel boring machine appears to be nothing more than an enormous rotating drill. But that description barely scratches the surface. In reality, a modern tunnel boring machine is one of the most advanced mobile engineering systems ever created. Every section of the machine performs a completely different task, and hundreds of individual systems must work together perfectly every second. If even one critical component fails, excavation can slow dramatically or stop entirely. Everything begins at the front of the machine, the cutter head. This massive circular structure slowly rotates against the rock face with tremendous force. Mounted across its surface are hundreds of hardened steel disc cutters, specially designed to fracture rock rather than simply cut through it. As each disc rolls across the surface, enormous pressure builds until the rock suddenly cracks apart. Instead of producing dust like a conventional drill, The rock breaks into manageable pieces that immediately fall into collection chambers behind the cutter head. Powering this process are gigantic hydraulic cylinders capable of producing thousands of tons of forward thrust. These cylinders push against the concrete tunnel lining already installed behind the machine, allowing the TBM to move steadily forward while maintaining exceptional stability. Every advance is carefully controlled, sometimes only a few centimeters at a time. Depending on geology, engineers constantly adjust the speed of rotation, thrust pressure, and cutter head torque to achieve maximum efficiency while minimizing wear. Once the rock has been broken apart, another engineering system takes over. A network of heavy-duty conveyor belts transports excavated material through the entire length of the machine before carrying it out of the tunnel. Some of the world's largest projects remove thousands of tons of rock every single day. Without this continuous transport system, excavation would quickly come to a halt. But perhaps the most remarkable part of the tunnel boring machine lies immediately behind the cutter head. As the machine moves forward, robotic installation systems begin assembling enormous precast concrete segments. Each segment weighs several tons. Using hydraulic lifting arms and automated positioning systems, the segments are carefully placed one by one to form a complete concrete ring around the tunnel. When the final locking segment is installed, the ring immediately becomes the permanent structural support for that section of the tunnel. Only after the entire ring has been completed can the hydraulic cylinders extend again and push the machine forward to begin the next excavation cycle. This entire sequence repeats thousands of times during a single project. Modern tunnel boring machines also function as intelligent engineering laboratories. Hundreds of electronic sensors constantly monitor cutter wear, hydraulic pressure, vibration levels, groundwater conditions, machine temperature, tunnel alignment, and surrounding ground movement. Every second, this information is transmitted to engineers inside the control room. Powerful computer systems analyze the data in real time, allowing operators to make immediate adjustments whenever geological conditions begin to change. Navigation is equally impressive. Many people assume that a machine weighing more than 2,000 tons would be impossible to steer accurately. The opposite is true. Laser guidance systems, gyroscopic sensors, GPS reference points, and advanced surveying equipment allow engineers to maintain extraordinary precision. Some tunnel boring machines complete journeys several kilometers long while remaining within only a few millimeters of their planned route. Different geological conditions require different types of tunnel boring machines. Hard rock TBMs are designed to excavate mountains composed of granite, basalt, and limestone. Earth pressure balanced machines carefully control pressure while tunneling beneath crowded cities built on soft soil. Slurry shield machines use pressurized slurry systems to stabilize water-rich ground beneath rivers, lakes, and coastal regions. Choosing the wrong machine for the wrong geology could dramatically increase costs and place the entire project at risk. Despite their enormous size, tunnel boring machines remain incredibly precise engineering tools. Every movement is calculated, every meter is monitored, every decision is based on thousands of real-time measurements. Together, these extraordinary systems allow engineers to accomplish something that once seemed impossible. They can carve safe, accurate tunnels beneath mountains, rivers, oceans, and some of the busiest cities on Earth with astonishing reliability. And yet, even this incredible technology cannot eliminate every danger waiting beneath the surface. Because no matter how advanced the machine becomes, nature always has the final challenge. For all of their incredible power, tunnel boring machines have one important limitation. They can never predict exactly what lies ahead. Everything hidden beneath the Earth's surface remains one of the greatest uncertainties in modern engineering. Geological surveys provide valuable information before construction begins, but they can never reveal every fracture, underground river, unstable rock formation, or hidden fault buried hundreds of meters below ground. Every tunnel is an exploration into the unknown. A machine may spend several days cutting smoothly through stable granite before suddenly encountering soft clay, fractured limestone, or water-saturated soil within only a few meters. When that happens, everything changes. Engineers must immediately reduce excavation speed, adjust hydraulic pressure, modify cutter head rotation, and carefully monitor every movement of the machine. A mistake made underground cannot always be corrected easily. Sometimes it cannot be corrected at all. One of the greatest dangers facing every tunnel boring machine is groundwater. Deep beneath the surface, Enormous quantities of water are trapped inside layers of rock under tremendous pressure. If the cutter head suddenly breaks into one of these underground reservoirs, water can rush toward the excavation face with incredible force. Without careful pressure control, thousands of liters of water mixed with mud and loose soil could flood the excavation chamber within minutes. Modern earth pressure balance and slurry shield tunnel boring machines were specifically designed to overcome this problem. By carefully balancing the pressure at the excavation face, engineers prevent surrounding soil and groundwater from collapsing into the tunnel. Maintaining this balance is one of the most difficult parts of tunnel construction. Too much pressure can damage equipment. Too little pressure can cause dangerous ground settlement above the tunnel. Every adjustment requires constant monitoring by experienced operators. Hard rock creates a completely different challenge. Although the cutter head is equipped with hundreds of hardened steel disc cutters, these components slowly wear down after continuously crushing granite and basalt. Some projects require thousands of cutter replacements before excavation is complete. Replacing these cutters is neither quick nor easy. Technicians often enter highly pressurized maintenance chambers located directly behind the cutter head. Inside these confined spaces, they carefully remove damaged cutters weighing dozens of kilograms before installing new ones. In certain projects beneath rivers or oceans, maintenance must even be carried out under compressed air to prevent water from entering the excavation chamber. These operations demand exceptional skill and strict safety procedures. Navigation presents another remarkable engineering challenge. A tunnel boring machine weighing more than 2,000 tons cannot simply turn like an ordinary vehicle. Instead, engineers guide its direction using powerful hydraulic steering cylinders, laser guidance systems, gyroscopic sensors, and continuous surveying measurements. Every few meters, the machine's position is compared against its planned alignment. Even a deviation of only a few millimeters may require immediate correction. This level of precision becomes especially important when two tunnel boring machines begin excavating toward each other from opposite ends of the same project. After years of continuous excavation, both machines must arrive at exactly the same location. In many famous projects, the final alignment error measured only a few millimeters despite drilling for several kilometers through mountains and complex geological formations. Protecting the surface above the tunnel is equally important. Many tunnel boring machines travel beneath residential neighborhoods, hospitals, airports, highways, and historic buildings. The ground above cannot be allowed to settle significantly. Engineers therefore install thousands of monitoring points across the construction area. Laser scanners, satellite positioning systems, vibration sensors, and settlement markers continuously measure the slightest movement. If unexpected settlement begins to appear, excavation immediately slows while engineers investigate the cause. Despite all these obstacles, tunnel boring machines continue advancing, meter after meter, day after day, sometimes for years without interruption. Each completed tunnel represents far more than an engineering achievement. It represents the successful combination of geology, mechanical engineering, structural design, computer science, surveying, and human experience working together beneath conditions few people will ever witness. Yet even after overcoming these extraordinary underground challenges, engineers continue pushing tunnel boring technology even further. Because the next generation of tunnel projects will be larger, deeper, longer, and more ambitious than anything humanity has attempted before. Every tunnel boring machine is built for a purpose. Some carve paths beneath crowded cities. Others pass through mountain ranges that once divided entire countries. And a few have achieved engineering milestones that changed transportation forever. One of the greatest examples is the Gotthard Base Tunnel in Switzerland. Stretching more than 57 kilometers beneath the Swiss Alps, it is the longest railway tunnel ever constructed. For generations, the Alps represented one of Europe's greatest natural barriers. Freight trains and passenger traffic were forced to travel across steep mountain routes that limited speed and capacity. Engineers envisioned something far more ambitious. Instead of climbing over the mountains, they decided to travel directly through them. Construction required multiple giant tunnel boring machines working continuously through some of the hardest rock formations on the continent. Temperatures deep inside the mountain often exceeded 40 degrees Celsius. Geological pressure constantly challenged both the machines and the engineers responsible for operating them. Years of excavation eventually connected two sides of the Alps with astonishing precision. Today, trains travel through the tunnel at speeds exceeding 200 kilometers per hour, dramatically reducing travel time while increasing the efficiency of European transportation. Another extraordinary achievement lies beneath the English Channel. The Channel Tunnel connects the United Kingdom and France through approximately 50 kilometers of underground railway, much of it located beneath the seabed. When construction began, many people questioned whether such a project was even possible. Engineers from 2 different countries started excavating from opposite directions. Working hundreds of meters below the surface, tunnel boring machines advanced day after day through complex geological formations. After years of continuous excavation, the 2 teams finally met almost perfectly in the middle. The alignment error measured only a few centimeters, an extraordinary demonstration of modern engineering precision. Today, millions of passengers and enormous volumes of freight move between Britain and continental Europe through a tunnel that once existed only as an ambitious dream. Beneath the world's largest cities, tunnel boring machines are quietly transforming urban life. Tokyo, Singapore, Shanghai, London, New York, and many other major cities continue expanding their underground transportation networks to reduce congestion above ground. Instead of building wider roads, engineers increasingly choose to build beneath existing infrastructure. New metro systems, underground highways, stormwater tunnels, utility corridors carrying electricity, water, communications, and district cooling systems. These invisible networks support millions of people every day without most citizens ever realizing they exist. Tunnel boring technology is also making possible projects that extend far beyond transportation. Hydroelectric power stations depend on deep water tunnels to generate renewable energy. Massive water transfer systems carry fresh water across dry regions. Flood protection tunnels divert enormous volumes of stormwater away from densely populated cities. As climate change increases the frequency of extreme weather events, underground engineering is becoming more important than ever before. Every successful project demonstrates how tunnel boring machines have evolved from simple excavation equipment into one of the most valuable engineering technologies ever created. Each completed tunnel saves time, improves safety, strengthens economies, and connects communities that were once separated by mountains, rivers, or vast distances. Yet these remarkable achievements may only represent the beginning, because engineers are already designing projects that will push tunnel boring technology even further. Longer tunnels, deeper tunnels, larger machines, and perhaps one day, entire underground cities connected by networks that future generations will simply consider a normal part of everyday life. For more than half a century, tunnel boring machines have transformed underground construction. Yet many engineers believe their greatest achievements are still ahead. The next generation of tunnel boring machines will not simply be larger. They will become smarter, faster, safer, and far more autonomous than anything operating today. Artificial intelligence is already beginning to change the way modern tunnel projects are managed. Instead of relying only on human experience, advanced computer systems can analyze millions of pieces of information every single minute. Ground pressure, rock hardness, machine vibration, hydraulic performance, temperature, groundwater levels, cutter wear. Every measurement is collected continuously, allowing engineers to identify changing conditions long before they become dangerous. Future tunnel boring machines may automatically adjust cutter head speed, hydraulic pressure, and excavation rates without waiting for human instructions. This could dramatically improve efficiency while reducing mechanical wear and lowering construction costs. Maintenance is also entering a new era. Replacing worn cutting discs has always been one of the most difficult and dangerous parts of tunnel excavation. In the future, robotic maintenance systems may perform many of these tasks automatically. Instead of placing technicians inside high-pressure chambers, remotely operated robots could inspect, replace, and repair critical components while reducing risks for construction crews. Digital twin technology is creating another major breakthrough. Every movement of a tunnel boring machine can now be recreated inside a virtual computer model. Engineers can simulate different geological conditions, predict equipment failures, and test construction strategies before making changes underground. Problems that once required expensive trial and error may soon be solved digitally before excavation even begins. Surveying technology is improving just as quickly. High-precision laser scanners, satellite positioning systems, and intelligent navigation software are allowing tunnel boring machines to travel with extraordinary accuracy over distances of many kilometers. Future projects may achieve even greater precision while reducing construction time. The ambitions of engineers continue to grow. Around the world, governments are planning deeper metro systems, longer railway tunnels, larger underground utility corridors, and massive flood protection networks capable of protecting entire cities from extreme weather. Some researchers are even studying the possibility of fully connected underground districts, where transportation, energy systems, communications, and public infrastructure operate almost entirely below the surface. Tunnel boring machines will play a central role in making these projects possible. As cities become more crowded and available land becomes increasingly limited, building downward may become just as important as building upward. The future of engineering is no longer measured only by the height of skyscrapers or the length of bridges. It is also measured by how intelligently we use the world beneath our feet. Every generation has built technologies that change civilization. The steam engine transformed transportation. Electricity transformed industry. The internet transformed communication. Tunnel boring machines may ultimately transform the hidden world beneath our cities. The next time you travel through a subway tunnel, drive beneath a mountain, or cross an underwater railway, remember that none of it happened by accident. It became possible because thousands of engineers refused to accept that mountains, rivers, and oceans were barriers that could never be crossed. Instead, they found a way to build straight through them. And the story of underground engineering has only just begun. For thousands of years, humanity has looked toward the horizon whenever we dreamed about the future. We crossed oceans. We climbed mountains. We built taller skyscrapers than anyone thought possible. Eventually, we even reached space. But perhaps the next great frontier has been beneath our feet all along. Every tunnel created by a tunnel boring machine represents far more than an engineering achievement. It represents another step toward a future where cities become larger without occupying more land, where transportation becomes faster without adding more highways, where critical infrastructure is protected from storms, extreme temperatures, and the growing challenges of climate change. Many of tomorrow's cities may not only expand upward, they may also expand downward. Hidden beneath busy streets could be entire transportation networks, energy systems, logistics centers, research laboratories, emergency shelters, and utility corridors working together in ways that most people will never see. The machines making that future possible are already operating today, quietly, patiently, me up there, be me up there. They continue carving paths beneath mountains, rivers, airports, in some of the busiest cities on Earth. Most people will never hear their engines. Most will never stand beside one of these incredible machines. Yet millions of lives are improved because of the tunnels they create. Every subway ride, every mountain crossing, every underground railway, every tunnel carrying clean water, electricity, communications, or flood protection begins with one extraordinary idea. That impossible obstacles can be overcome through engineering. Tunnel boring machines are not simply the largest drilling machines ever built. They are symbols of human curiosity, determination, and innovation. They remind us that the greatest engineering achievements are often the ones hidden from view. As technology continues advancing, the tunnels of tomorrow may become longer, deeper, and more ambitious than anything we can imagine today. Perhaps one day, future generations will travel through underground cities that stretch for hundreds of kilometers. Perhaps they will consider living beneath the earth just as ordinary as living above it. And when that future arrives, history may remember the tunnel boring machine as one of the inventions that quietly changed civilization forever. So before we finish this journey, here's one final question. If engineers built a safe, modern city entirely beneath the Earth's surface, would you choose to live there? Share your answer in the comments below. And if you enjoy exploring the world's greatest engineering marvels, don't forget to subscribe, because our next journey is already being built beneath the surface.